Right now, somewhere in our galaxy, a star is being stretched, shredded, and swallowed by an object so dense that not even light, the fastest thing in existence, can escape it. If you cross the boundary of a black hole called the event horizon, you would not feel a single thing in that moment. Yet you would have crossed the point of no return forever. What actually happens inside a black hole beyond the point where our telescopes, our mathematics, and our physics break down completely. I remember the first time I saw the Event Horizon Telescope's image of a real black hole, that glowing orange ring around total darkness, and felt something shift in my understanding of what is real. Every generation of scientists who studied black holes, from Einstein, who predicted them mathematically, to Hawking, who dedicated his life to them, was humbled by how much they reveal about the limits of human knowledge. In 2025 and 2026, new observations and simulations have pushed our understanding of black holes further than ever, and what science is finding is stranger than any science fiction. Today, the real documented science will show you exactly what black holes are, what happens at each layer as you approach and cross one, and what physics predicts and fails to predict about their interiors. What the headlines are not telling you is that the Event Horizon Telescope released new images in 2024, and gravitational wave detectors have now recorded the mergers of dozens of black holes, rewriting what we thought we knew. Welcome back to Tomorrow's Science. Let's dive in. A black hole is a region of space where gravity has become so extreme that the escape velocity exceeds the speed of light, making it impossible for anything, including light itself, to leave. The most common type forms when a massive star, many times the mass of our sun, exhausts its fuel, collapses under its own gravity, and triggers a supernova explosion that leaves behind an impossibly dense core. There are three main types: stellar black holes, a few times the mass of the sun; intermediate black holes, hundreds of times larger; and supermassive black holes at the centers of galaxies that can contain billions of solar masses. Before you even reach the black hole, you encounter the accretion disk, a swirling ring of superheated gas and dust spiraling inward at nearly the speed of light, glowing hotter than the surface of most stars. Just outside the event horizon sits the Photon Sphere, a zone where gravity is so strong that light itself travels in circles, meaning if you stood there, you could theoretically see the back of your own head. If you fell into a supermassive black hole feet first, you would feel no dramatic jolt at the event horizon. General relativity predicts you would cross it without any immediate sensation of transition. To an outside observer watching you fall in, time dilation would cause you to appear to slow down and freeze at the event horizon, your image fading and redshifting into invisibility. You would never appear to fully cross. For a smaller black hole, the tidal forces become extreme before crossing, gravity pulling your feet so much harder than your head that your body would be stretched into a long, thin stream of matter, a process physicists actually call spaghettification. Once inside the event horizon, the laws of physics as we understand them begin to break down. Space and time swap roles, and the singularity at the center is not a place in space, but a moment in your future you cannot avoid. At the very center lies what mathematics calls the singularity, a point of theoretically infinite density, where our equations produce infinities and simply stop giving meaningful answers. Most physicists believe the singularity is not a real physical object, but a sign that our current theories are incomplete, a gap in human knowledge waiting for a future theory that unifies gravity with quantum physics. In 1974, physicist Stephen Hawking made one of the most surprising predictions in science. Black holes are not truly black, they slowly emit a faint thermal radiation from their outer boundary due to quantum effects. Over an almost incomprehensibly long time, far longer than the current age of the universe, A black hole slowly loses mass through this radiation, and eventually, theoretically, evaporates completely. This raises one of the deepest unsolved problems in physics. If a black hole evaporates, what happens to all the information about everything that ever fell in? Is it destroyed, or does it somehow escape? In 2019, the Event Horizon Telescope, a global network of radio observatories linked together to form an Earth-sized telescope, captured the first ever direct image of a black hole's shadow. The image showed M87's black hole, 6.5 billion times the mass of our Sun, as a glowing orange ring around a dark shadow, confirming predictions made by Einstein's equations more than a century earlier. In 2022, the same telescope captured the black hole at the center of our own Milky Way, Sagittarius A, proving that a black hole, 4 million times the mass of our Sun, sits at the heart of our galaxy. In 2015, the LIGO detector picked up the faint ripple in spacetime produced by two black holes merging 1.3 billion light-years away, confirming a prediction that had stood untested for a century. Each black hole merger detected by LIGO and Virgo gives us a precise measurement of the masses, spins, and distances involved, allowing scientists to test general relativity under the most extreme conditions in the universe. Gravitational wave astronomy has opened an entirely new way of observing the universe, one that does not rely on light at all, allowing us to detect events in regions too dark and distant for any telescope. Near a black hole, time itself slows. A clock placed close to the event horizon would tick measurably slower than one far away, a real effect that GPS satellites must account for in their calculations every single day. The gravity of a black hole bends light so powerfully that a single black hole can act as a lens, magnifying, distorting, and duplicating the images of entire galaxies behind it in a phenomenon called gravitational lensing. The most powerful jets of energy ever observed, quasar jets stretching millions of light-years and outshining entire galaxies, are powered by supermassive black holes consuming matter at the center of those galaxies. Black holes are not just cosmic curiosities. They are the places where the known laws of physics reach their absolute limits, pointing toward a deeper understanding of reality that science is still working to uncover. I want to hear from you. Does the idea of a black hole make you feel terrified by the unknown? Or does it fill you with wonder at how much the universe still has left to show us? Leave your answer in the comments and subscribe to Tomorrow Science, so you never miss our next deep dive into the greatest unanswered questions the universe has left for us.